Welcome to Draw the Logic. Today we answer one deceptively simple question. How does a machine understand that the words apple and banana are related, but apple and loan are not? To a plain computer, without embeddings, all words look the same, just distinct symbols. Apple, banana, and loan are all equally far apart. There is no sense that apple and banana are more alike than apple and loan. We will move through 6 stages. First, the foundations, turning words into vectors and measuring similarity. Then classic static embeddings like Word2Vec and Glove. Then the contextual revolution powered by transformers and BERT. Then sentence embeddings and the loss functions that shape them. Then multimodal and large-scale embeddings. And finally, how real systems search billions of vectors in milliseconds. Say our entire vocabulary has just 6 words: cat, dog, apple, banana, loan, and bank. Each word is assigned one fixed index. The word apple becomes a vector as long as the vocabulary, with a single one at apple's position, and zeros everywhere else. This is called a one-hot vector. But real vocabularies contain tens of thousands, even millions, of words. Every single word needs its own giant vector. And every vector is almost entirely zeros. This is extremely sparse and extremely wasteful. Worse still, any two one-hot vectors are always orthogonal to each other. Their dot product is always 0. No matter how semantically similar apple and banana actually are, the vectors carry no signal of that relationship. This is exactly the problem embeddings were invented to solve. Here's an intuition you already use. If two people share the same friends, hobbies, and hangouts, you assume they're probably similar people. Even without meeting them, you're judging them by the company they keep. The linguist John Firth put it precisely: you shall know a word by the company it keeps. Cat and dog show up in almost identical sentences. So a model that reads enough text learns they must be semantically related. In practice, this means scanning a huge corpus of text, counting which words co-occur near each other, and then mapping every word to a vector such that words with similar contexts end up close together in space. That's the entire foundation of embeddings. An embedding replaces that giant, mostly empty one-hot vector with a short, dense vector. Every value is meaningful, typically just 50 to 300 numbers instead of tens of thousands. When we plot these dense vectors, even compressed down to just 2 dimensions for visualization, animals cluster together, fruits cluster together, and finance words cluster together. Geometry now encodes meaning. Here are the embedding vectors for cat and dog. To measure how similar 2 words are, we look at the angle between their vectors. A small angle means the vectors point in nearly the same direction. High similarity. Mathematically, this is the cosine similarity formula. The dot product of the 2 vectors, divided by the product of their magnitudes. This normalizes away vector length, so only direction, meaning, matters. Say cat is the vector 0.8, 0.6, and dog is 0.9, 0.4. Their dot product is 0.96. Dividing by their magnitudes gives a cosine similarity of about 0.98. Very close to 1. Meaning these 2 words are highly similar. Word2Vec learns entirely from a sliding window of nearby words. Here, fox is our target word, and quick, brown, jumps, over, form its surrounding context. The continuous bag of words model, or CBOW, averages the vectors of all context words and uses that average to predict the target word. Fox. It is fast, and works well for frequent words. Skipgram flips the direction. It takes the single target word, fox, and tries to predict each surrounding context word. Independently, it needs more training examples per sentence, but produces noticeably better embeddings for rare words. The original skipgram objective needs a full softmax over the entire vocabulary, with 50,000 words. That means recomputing 50,000 scores for every single training example. This is far too slow to scale. Negative sampling reframes the problem. Instead of scoring the whole vocabulary, the model just learns to tell apart a real observed pair, like fox and quick, from a handful of random, fake pairs drawn from noise. It becomes simple binary classification. The objective pushes up the score of the real pair through a sigmoid, while pushing down the scores of just 5 to 20 negative samples. Now only a tiny handful of word vectors are updated per step, instead of the entire vocabulary. Training becomes dramatically faster. GLOVE starts from a different question. Instead of predicting neighbors, look at global co-occurrence ratios. Compare how often ice and steam each appear near a probe word. Near solid, the ratio is huge. Clearly ice related. Near gaseous, it's tiny. Clearly steam related. Near neutral words like water or fashion, the ratio settles near 1. GLOVE turns this into a concrete training objective. The dot product of a words vector and a context words vector, plus 2 bias terms, should approximate the logarithm of how often they co-occur across the entire corpus. It's trained with weighted least squares so extremely frequent pairs don't dominate. Word2Vec and GLOVE treat every word as one atomic unit. If a word never appeared during training, a rare word, a typo, a made-up word, there is simply no vector for it at all. Fast text instead breaks every word into overlapping character n-grams where becomes wh, we, her, ear, and re, each with its own vector, plus a vector for the whole word. Now, even a completely unseen word like wherewithal can be embedded. We simply sum the vectors of the subwords it shares with words we've seen. This is why fast text handles typos, rare words, and rich morphology so well. Embeddings encode semantic traits as directions. Here, moving right means more royal, and moving up means more feminine. Let's place king and man in this space. Subtracting the vector for man from king cancels out the male-ness, leaving behind something close to the pure concept of royalty. Now add the vector for woman. Remarkably, the resulting point in space lands almost exactly where the vector for queen actually sits. This is the famous king minus man plus woman equals queen relationship. A striking demonstration that these geometric directions capture real semantic meaning. But researchers have found this needs an honest caveat. The nearest neighbor search typically has to explicitly filter out king itself. And this trick performs best on gender analogy specifically. It performs far less reliably on other kinds of relationships. It is a useful heuristic, not a guaranteed law of the vector space. This idea reaches far beyond text. Tabular data has categorical columns too. Store ID, day of week, zip code. Traditionally, these are one-hot encoded, which explodes into huge, sparse, meaningless columns with no notion of similarity. Entity embeddings solve this by learning a small dense vector for each category, trained jointly with the actual prediction task. In the Rossmann sales competition, this let day of week embeddings automatically discover that Saturday and Sunday behave alike, clustering weekends apart from weekdays, which boosted the accuracy of downstream models like gradient-boosted trees. Here is the fundamental flaw of every static embedding we've seen so far. The word bank means a riverbank in one sentence, and a financial institution in the other. But Word2Vec, GLOVE, and fast text all assign it the exact same fixed vector, regardless of context. What we actually need is a dynamic representation. One vector for bank near a river, and a completely different vector for bank near a loan. This requires the model to read the whole sentence before deciding on a word's meaning. That is exactly what transformers deliver. Inside a transformer, every token, including bank, is projected into 3 vectors: a query, a key, and a value. The query asks, what am I looking for? And the keys let every other token answer, here's what I offer. The model computes an attention weight between bank and every other word. Here, bank attends strongly to approved and loan, and only weakly to the and today. Aggregating information from approved and loan shifts bank's hidden state away from a neutral starting point and directly into the financial region of the space. In the river sentence, it would shift the opposite way. This is what makes an embedding truly contextual. BERT's first pre-training task is masked language modeling. Random tokens in a sentence are hidden, and the model must predict them using context from both the left and the right simultaneously. A truly bidirectional view that earlier models like GPT couldn't achieve. The second task, next sentence prediction, gives BERT two sentences and asks a simple binary question. Does the second sentence actually follow the first in the original text? This helps the model learn relationships that span across sentences. A typical BERT-based model stacks 12 of these self-attention layers, each working with a hidden size of 768. The result: every single token gets its own contextual vector, shaped by the entire sentence around it. Standard BERT is superb at comparing two specific sentences directly, a so-called cross-encoder. But to compare 10,000 sentences against each other, you'd need nearly 50 million forward passes. This is far too slow for real-time search. What if we just average BERT's token outputs? Surprisingly, this performs worse than even the much older, much simpler trick of averaging static globe vectors. Raw BERT wasn't trained to produce good sentence-level geometry. SBERT solves this with a Siamese twin tower structure. Two sentences are each passed independently through the same BERT model, then pooled into a single fixed-size vector. Because the towers share weights, the vectors can then be compared directly with fast Cosine Similarity. No pairwise computation needed. Mean pooling, simply averaging every token vector, turns out to be the most robust default choice, scoring 87.4 on standard benchmarks. The CLS token needs task-specific fine-tuning to be competitive, and max pooling generally performs the worst of the three. Triplet loss works with three examples at once: an anchor sentence, a positive sentence that means the same thing, and a negative sentence that doesn't. The training objective enforces a margin. The negative must be pushed further from the anchor than the positive, by at least a fixed amount alpha. Training gradually reshapes the embedding space to satisfy this constraint. Random triplets are almost always easy. The negative is naturally far away, producing zero loss and teaching the model nothing. Semi-hard triplets sit just inside the margin. But hard triplets, where the negative is actually closer than the positive, give the strongest, most useful training signal. Contrastive learning trains on batches of matched pairs. A query and its correct answer. The clever trick: every other answer already sitting in the batch automatically becomes a negative example for this query, at zero extra cost. Every query is scored against every answer in the batch, forming a similarity matrix. Training pushes the diagonal, the true, matching pairs, as high as possible, while pushing every off-diagonal, mismatched pair down. This is the InfoNCE loss, the engine behind CLIP, SimCLR, and SimCSE alike. In retrieval systems, this is often called multiple negatives ranking loss. Mathematically the same idea, scaled to batches of thousands of negatives with a temperature parameter controlling how sharply it separates matches from non-matches. CLIP trains an image encoder and a text encoder together from scratch, on hundreds of millions of image caption pairs. Both project into the same shared embedding space. So a photo of a dog and the text, a photo of a dog, can be compared directly. Training computes the dot product of every image embedding with every text embedding in the batch, forming a similarity grid. The symmetric InfoNCE loss maximizes the diagonal correct pairs, while minimizing every off-diagonal mismatched combination. Because the text encoder understands open vocabulary, CLIP can classify an image just by comparing it against arbitrary text descriptions of classes, with no task-specific fine-tuning at all. This is zero-shot classification, and it generalizes to almost any visual category imaginable. Modern generalist embedders like NV-Embed and Grit-LM are built on decoder-only LLMs, models like Llama and Mistral. But these models normally use a causal mask, so a token can only see what came before it, never what comes after. For embeddings, that's a real limitation. Advanced embedders strip out that causal mask during fine-tuning, add sophisticated pooling layers instead of relying on just the final token, and prepend instructions like, represent this query for medical search, dynamically biasing the model toward the task at hand. Matryoshka representation learning trains a single model so that truncated prefixes of its output vector remain useful on their own. Like nested Russian dolls, a developer can slice a 3072-dimension vector down to just a few hundred dimensions, dramatically cutting storage costs, while barely losing any retrieval accuracy. At enterprise scale, a vector database might hold billions of embeddings. Comparing a single query against every one of them exactly is computationally impossible at the latencies real applications require. Vector databases solve this with approximate nearest neighbor indexing by deliberately sacrificing a small amount of recall, occasionally missing the single best match. They achieve exponential speedups, answering queries in sub-millisecond time. HNSW builds a hierarchy of graphs. Search starts at a sparse top layer of highway nodes, quickly narrowing down to the right neighborhood, then routes downward into denser layers for precise results. It achieves excellent recall and handles new inserts gracefully, but demands a lot of memory for its graph edges. IVF-flat takes a different approach. It partitions all vectors into clusters using k-means. Then at query time only scans the cluster whose centroid is closest. This gives extremely fast, memory-efficient search, though recall can degrade over time as data drifts, requiring periodic rebuilds. Product quantization takes a third approach, splitting vectors into small chunks and mapping each chunk to a learned codebook, achieving massive compression. Great for archiving cold data, at the cost of some precision. Every indexing algorithm makes its own trade-off between memory, speed, and recall. The bi-encoder, or two-tower model, encodes queries and documents completely independently. Millions of document vectors are indexed offline. At query time, only the query passes through its tower. Then a dot product against the index gives millisecond results. But compressing a whole document into one vector loses fine-grained detail. The cross-encoder concatenates query and document and runs them jointly through full self-attention, letting every token see every other token. This gives state-of-the-art accuracy. But every single candidate document needs its own full forward pass, completely unscalable for searching millions of documents directly. Colbert bridges the gap. Instead of one vector per document, it keeps every token's vector, and at query time computes the maximum similarity between each query token and any document token, the max-sim operator. This lets Apple Computer correctly latch onto the technology sense of Apple, distinguishing it precisely from apple fruit. As dimensionality grows, something strange happens. The distances between random points converge tightly to a single value. The ratio between the nearest neighbor and the farthest point rapidly approaches 1. Every point starts looking equally close, or equally far, destroying the very notion of a nearest neighbor. At the same time, the volume of a high-dimensional sphere collapses relative to its bounding cube. In 2 dimensions, a circle fills most of its square. In high dimensions, that same sphere becomes vanishingly small. Nearly all the data migrates out to the corners and edges of the space. High-dimensional geometry also produces hubs, points that appear as neighbors to almost everything, and anti-hubs that appear as neighbors to nothing, hurting retrieval accuracy. So why do embeddings still work in practice? Because contrastive training forces real text data onto a much lower dimensional, structured manifold, rather than spreading it uniformly through the vast empty space. Dense embeddings excel at conceptual meaning, but they compress text into a continuous space, which can silently drop exact, specific tokens, product codes, legal citations, precise error codes. There's no guarantee the exact string survives compression. Sparse retrieval, like BM25, builds an inverted index across the entire vocabulary and guarantees exact keyword matches, but fails completely on synonyms because dense and sparse retrieval fail in completely different, orthogonal ways. Modern systems query both indexes in parallel. Dense Cosine scores and sparse BM25 scores live on completely incompatible scales, so naive score blending fails. Reciprocal rank fusion sidesteps this entirely. It discards the raw scores and combines results purely by their rank position. Documents that appear near the top of both lists rise to the very top of the final result. Let's recap the entire journey. One-hot vectors were sparse and orthogonal, carrying no meaning. Dense embeddings placed meaning directly into geometry. Word2Vec, Glove, and fast text learned those static vectors from raw text. Transformers and BERT made vectors dynamic and context-aware. SBERT and metric learning made sentence-level search fast and accurate. CLIP and LLM-based embedders unified images, text, and massive scale. And vector databases with hybrid search make all of it searchable in milliseconds. across billions of items. From a single one-hot vector all the way to billion-scale semantic search. You now understand exactly how machines represent and retrieve meaning. If this was helpful, please like and subscribe. It really helps this channel. See you in the next one.